priority scheduling algorithms, once a process gets a priority based on its priority number, the general rule is that the next process to be scheduled is the process with the highest priority. If we have more than one process with the highest priority, we should pick the one that arrived first in the ready queue, such that we minimize also the average waiting time. Let's move on to preemptive scheduling algorithms. The process can be preempted while executing its CPU burst. Because a new process with better credential got in the ready queue, or for other reasons like the fact that the quantum expired. In that case, the process gets back at the end of the ready queue and waits for being rescheduled. One disadvantage when it comes to preemptive scheduling algorithms is that they have much more full context switches. So every time when we switch between two different processes, we have a full context switch, which sometimes might be take a considerable amount of time. This full context switch, in reality, it's added in the Gantt diagram. We don't consider the size of any full context switch in our Gantt diagrams. So let's start with the shortest remaining time. Shortest remaining time, it's in fact the preemptive version of shortest job first. In the beginning, the process with the shortest CPU burst is scheduled. If there is a tie, then pick the one with the earliest arrival time. If while the process executes, another process arrives in the ready queue, then we're going to have an interrupt. The scheduler compares the remaining time of the interrupted process with the CPU burst of the new process. If the remaining time is less or equal than the CPU burst of the new process, the already scheduled process continues its execution. Otherwise, the process is preempted and the new arrived process is scheduled. So here we have our time axis. We have the arrival time for the 5 processes. At moment 0, okay, so let's first talk about the Gantt diagram. So I'm going to have the Gantt diagram on one row, and here I will keep track of the remaining times and of the CPU burst. So at moment 0, we have only process 1 in the ready queue. We don't, no specific algorithm is going to be ran. Process 1 is going to be scheduled and it's executing until a new process arrives in the ready queue, which happens at moment 2. Now the remaining time for process 1 is of 1 unit. Remember that process 1 has a 3-unit CPU burst. On the other hand, the CPU burst of process 2 is 6. The scheduler checks 1 with 6. The remaining time of process 1 is smaller, so the process 1 continues the execution, and by our numbers, process 1 terminates at moment 3. At moment 3, in the ready queue, there is no other process. So besides process 2, keep in mind process 1 terminated. So process 2 starts the execution, and its execution is interrupted when a new process, process 3, arrives. At this moment, the remaining time for process 2 is 5. It executed for 1 unit. The CPU burst of process 3 is 4. So process 2 is going to be preempted and process 3 will be scheduled. Sorry. Okay. So process 3 starts at moment 4. It has a CPU burst of 4. It's going to execute until another process arrives in the ready queue, which is process 4. The remaining time at this moment at 4 for process 3 is going to be 2. It started with 4, executed 2 units, we have 2. Process that arrives has a CPU burst of 5. So process 3 has a better time and it's going to continue the execution until 8 when process 3 terminates. At moment 8, process 5 arrived in the ready queue. Again, whenever a process arrives in the ready queue, if at the same time we need to take a scheduling decision, consider first that process is in the ready queue, it's already in the ready queue, and then decide which process will go next. So at moment 8, we have process 5 in the ready queue with a CPU burst of 2, and then we have process 4 with a CPU burst of 5, and then we have process 2 with a remaining of 5. So process 5 has the shortest CPU burst, and it's going to be scheduled and it's going to execute until it terminates, which is at moment 10. So now we are left with process 2 and process 4. Both of them, they have the same time. However, we're going to pick the one that arrived first. So process 2 is the one that arrived first. It's going to be scheduled at 10, executes until 15, and then we are left with process 4 that will execute from 15 to 20. When it comes to the advantages and disadvantages of this scheduling algorithm, they are very similar to the shortest job first. One of the advantages is that this scheduling algorithm gives the optimal average waiting time among all the preemptive scheduling algorithms. When it comes to disadvantages, again, it's very hard to be implemented at the level of the CPU, because it's very hard to predict in advance what is the CPU burst of a process. Besides that, the shortest remaining time will give priority to short processes and can create starvation for large processes. Let's move on to a very known, popular scheduling algorithm, which is the round-robin scheduling algorithm. This algorithm is used a lot in a time-sharing environment. Based on this algorithm, a process cannot execute more than a fixed quantum of time. Again, the quantum of time is usually order of hundreds of milliseconds. The round robin has the advantage, let's say, that it's very fair when it comes to sharing the CPU time among different processes, because every process has the chance to execute for a unit of time, for a quantum of time. After that, it's preempted and it's gonna go back to the ready queue. So if we have 3 processes, for example, already in the ready queue, they're gonna go 1, 2, 3, 1, 2, 3, 1, 2, 3. In terms of disadvantages, well, when it comes to round robin, we have a lot of full context switches. And these context switches, they are adding to the Gantt diagram. So the round robin is not having a very good average waiting time or a very good average turnaround time. Actually, it has poor average waiting time and average turnaround time, because every process can execute a little bit, then it has to wait in the ready queue until everybody else executes a little bit, then it's going to be scheduled again for a short time, then it has to wait until all the others execute as well for a quantum, and so on. Okay, I picked an example when the quantum is 1. That means that we're gonna have full context switches almost after each unit of time. So it's basically the worst scenario possible, because we're gonna have a lot of full context switches. Just think about having this full context switch delay added to all these changes. Okay, so we're gonna use the same information that we have right here in our table, and I regret that I didn't also move it right here somewhere, but I'm not gonna do it now. You can write the table and just take a look at the table. At moment 0, we have process 1 in the ready queue, and process 1 will execute until process 2 arrive. So this is a very special case. Process 1 should execute just for one quantum of time, for a quantum of 1, because that's what we decided. But again, if there is nobody in the ready queue, then there is no need to run a scheduling algorithm. So we don't know in advance, and once the process is scheduled, should be free to execute until the decision is to be done, which means until a new process arrives in the ready queue. So here we have a special case, because between 0 and 2, there is no other process in the ready queue. So process 1 executes until moment 2, and then the process 1 is preempted. That's why I put the 1 in here. For me, what follows after the straight line represents what is in the queue after the full context switch. And what is before is to the left, it's what is before the full context switch. So at moment 2, again, first we consider that process 2 is already in the ready queue. Process 1 is preempted, process 2 is scheduled, executes from 2 to 3. At moment 3, process 2 finishes its quantum. In the ready queue, we have process 1. Process 1 will start running, process 2 goes back into the ready queue. At moment 3, process 1, process 2 goes back into the ready queue. Now we have process 1 executing. It's executing from 3 to 4, and at 4, process 1